Hello students, so in this video we'll focus in on showing you some more details of three components of the Zeeman effect experiment: the magnet, the polarizer, and the Fabry Pro. So these will be the elements. Here's the magnet, of course, here's the polarizer, here's the Fabry Pro etalon. So zooming on the magnet, just to give you a little details of what you will see here. I think in this camera view you can just barely see the copper windings in here, and they're all wrapped around these big pieces of metal here. So they sort of have a solenoidal shape, and you know when you run a current through a solenoid, there's a very strong magnetic field that is produced in the inner core of the solenoid. So the magnetic field is enhanced by these pieces of metal, and the magnetic field is sort of routed to appear on these two poles of the magnet here. So one will be the north pole, one will be the south pole. I don't know which is which, but it doesn't matter very much. And what you'll notice, of course, is that cadmium lamp, which we mentioned in the last video, is positioned right in the poles of the magnet. So the cadmium lamp will experience the magnetic field created by this electromagnet field. That's sort of the magnet there. The very next element is the polarizer. Let me move in a little bit more on the polarizer here so you can see what it does here. So the light basically comes in this side of the polarizer, and you can see that little white hash mark on the top here. And as we mentioned in the last video, the white hash mark is an indicator of the transmission axis of the polarizer. So if an electromagnetic wave that comes into the polarizer has an electric field component oscillating parallel to this hash mark, then that electromagnetic wave will be allowed to pass. So in this case here, because the hash mark is pointing straight up, electromagnetic fields that are polarized sort of up and down in this way will be allowed to pass. But of course the polarizer, we can rotate it, and so if I rotate it something like this, you can see I'm changing the position of the little hash mark right there. So if I go all the way over into this position here, then those vertically polarized electromagnetic waves will not be allowed to pass, but horizontally polarized electromagnetic waves will be allowed to pass. So these will be electromagnetic waves whose electric field component is polarized parallel to the floor, for example, or parallel to the tabletop. So that's what the polarizer does, and we can totally rotate it, but we're always keeping our eye on this little hash mark here as we take our data. So as we discussed the Fabry Pro, if the hash mark is always up, we'll call that vertically polarized light. If it's this way, we'll call it passing horizontally polarized light. In videos, it won't always be possible to see the little hash mark on the polarizer. So vertical and horizontal, and those will be the important settings for the Zeeman. The last of these sort of really important aspects of the Fabry Pro Zeeman is, of course, the Fabry Pro etalon. It's kind of unremarkable what it does. It just sort of looks like this, and you can see it highly reflecting coating in there, and it's of course labeled etalon. You sort of see through it. So what it is in structure is two very, very parallel pieces of glass. So it's constructed so that the front and back face of the etalon, in other words, that face and this face, are very parallel to each other. And the reason why you see it reflecting so much light like that, so much reflectance on the Fabry Pro itself, is because the inner surfaces of those plates are coated with a very highly reflecting material that reflects something like 99% of the light to maintain light in the inner annals of the cavity here. So we do lose a lot of light in using a Fabry Pro, but by having such a high reflectance is what makes the Fabry Pro such a high resolution interference device. So there's something called the resolving power, which is lambda over delta lambda. It is the following quantity. If you're trying to measure a wavelength of some lambda, the uncertainty in the lambda that you're able to resolve, in other words, delta lambda, for this device is about 1 million. So lambda over delta lambda is about 1 million. Meaning that the spread in wavelengths you can resolve with the Fabry Pro will be about 1/1,000,000th of the wavelength itself. So it's a fantastic device. So look up resolving power in optics if you need to on the web, but that's sort of what it is for the Fabry Pro.